Hey everyone, this is Josh. In this video we will be discussing another reaction synthesis. This example is particular to organic chemistry 2 in the material taught in that class. So let's go ahead and scroll down here. This was a question submitted to us from some sort of practice exam. The question is, which of the following synthesis schemes will result in a symmetric ether? So your goal is to choose which of these responses, which of these reactions with the given chemical reagents will result in a symmetric ether. So I'll go ahead and let you pause the video at this point, and then we will discuss each example. Great. So hopefully you're able to give that an attempt. Let's start with option letter A first. You're given a carboxylic acid and you're reacting it with an alcohol in the presence of a strong acid, in this case just labeled H+. This reaction I have over here to the right is titled acid catalyzed esterification. This is a reaction that, if not already, you'll be very familiar with as you progress through organic chemistry 2. So I decided to include the reaction scheme for acid catalyzed esterification. You can go ahead and look at that. The only things that I really want to point out is this alcohol group, or OH group, that's originally part of the carboxylic acid, ultimately leaves over here as a leaving group. And so what we see over here down towards the end of our reaction, this intermediate right here, that oxygen attached to an ether group, 2 carbons, is actually this alcohol that you were given as one of your starting materials, as one of your starting reactants. So that's really just what I wanted to point out there. Most, or not most, but a lot of reactions that you learn in organic chemistry 2 with using carboxylic acids or forming esters or amides and things of that nature have very similar chemistry to what's shown here in this arrow pushing mechanism. And so for option number A that we're discussing, this right here is the answer. That would be the compound that would result from the materials that you provided in that option, which is an ester. It's not even an ether, so it does not satisfy what we're looking for as far as it being a symmetric ether. So let's look at option number B now. You're given an alkyl halide as your starting material. Okay, and you're reacting it with magnesium in the presence of ether, something like diethyl ether, and you're also going to add an alcohol, an ethyl alcohol, not ethyl alcohol, an ethyl alcohol, sorry. So I'm going to go ahead and scroll over again. Simply, this reaction is just a preparation of Grignard reagent, and then you're using it on an alcohol. What I've provided here is the reaction scheme that I was once shown for the preparation of a Grignard reagent. This particular reaction scheme isn't pivotal to memorize. Just know that if you're adding magnesium with diethyl ether to an alkyl halide, you're going to be forming a Grignard reagent, which we know can do a lot of chemistry. And so for letter B, your resulting product will be that compound right there, which is ethane, which once again is not an ether, let alone a symmetric ether. Before I move on to option number C, actually let's move on to option number C, and then we can discuss what I was about to say. So this is your starting material here. You're reacting it with an alcohol, and you're also reacting it with a strong acid. Once again, this chemistry is very similar to the chemistry we discussed in option number A. Like I said, this kind of chemistry, this kind of arrow pushing mechanism right up here, very common, or at least there's a lot of reactions that are similar to this where a carbonyl carbon, such as, I'll use a different color, green, such as this carbon right here, will ultimately be attacked, like we see in this arrow pushing mechanism. So something like acid catalyzed esterification, and being able to recognize when you have a carbonyl, that's a strong skill to be able to have if you're going through organic chemistry too, and it'd be smart to review reactions that involve carboxylic acids and esters and things like that. So down here, jump back down here with this green arrow. There again is what we see in option number C. There's your starting material. You have your strong acid and your alcohol. And I'm not going to go through the chemistry because you can look above at the acid catalyzed esterification and be able to deduce that. But I want to point out that this right here is ultimately your product to that reaction. And again, not an ether, let alone a symmetric ether. So option number D, you're started with an alcohol, 2 moles of it, and you're reacting it with sulfuric acid right here with heat, relatively high heat. So this reaction is the acid catalyzed formation of an ether, as I've labeled right here, that I'll point to in red. So acid catalyzed formation of ether. This is a great reaction for creating ethers, obviously. In the first step of the reaction, you have the electrons on your alcohol pulling off a hydrogen of your strong acid, which is sulfuric acid. So now you have a protonated ether right here. Another alcohol that you have in solution right here will come in and backside attack, forcing this to leave as a water. And now you have this intermediate right here, which is starting to look like what we want. And ultimately that hydrogen will be pulled off of that oxygen. This will leave, as I've indicated right here. And acid catalyzed formation of ether, just like it states in the name, will give us an ether as our product, which is that right there that I've drew in blue and just circled in red. So we were able to form an ether with the material that we provided in letter D. And not only is it an ether, but it is a symmetric ether. We have 2 carbons on both sides of our oxygen. So ultimately, letter D is the correct answer to this question. But we'll go ahead and talk about letter E just while we're here, just for our benefit. Letter E is a good one. This goes back to one of the primary reactions that we learned back in Organic Chemistry 1. It's sometimes called Williamson ether synthesis, or just SN2 chemistry. We have a alkyl halide, in this case has a chlorine on it, and you have a strong base due to the sodium that was added, and there's also ethanol in solution. This strong base will go ahead and backside attack our primary alkyl halide, which favors SN2 chemistry. When we have an alkyl halide in the presence of a strong base, which is a strong nucleophile, it will favor SN2 chemistry, and that's what we see happening here. And the chlorine leaves with its electrons as a leaving group, and so we're given this as the product, which is an ether, but it is not a symmetrical ether. We have 1, 2 carbons on this side, and 1, 2, 3 carbons on this side of the oxygen. So there it is. There's each reaction that was provided, and ultimately letter D is your answer. Thank you for providing this question. Hopefully that helped.